Let's take a look now at the association kinetics and thermodynamics for micelle-like structures, and we're going to do this in a pretty crude way. So let us suppose that there is some rate for association of these structures given by some association constant times the concentration of monomers raised to the nth power to form an aggregate of n molecules. Remember that when we write rate equations, if two units of something have to come together, we square the concentration, 3 units we cube it, and so on. So we need the concentration raised to the nth power in this association equation if we form an aggregate from monomers x1 consisting of n particles. Conversely, once the particles come together in an aggregate, they will dissociate at some rate given by another constant times the concentration of aggregates. So this is the mole fraction of aggregates. But we must divide this by the number of particles in each aggregate, because each one of these dissociation events will give n monomers. In equilibrium, the association rate is equal to the dissociation rate. Now we've normalized to monomers. And so, therefore, we can set these two equations equal, with the result then that the equilibrium constant for the dissociation, which is the ratio of the association and dissociation constant, is given by x n over n x1 to the power n. Solve this equation here for x1, and notice that the total concentration has to be equal to the concentration as a mole fraction of monomers plus the concentration of aggregates. So we can therefore express xn as equal to C minus x1. But notice that the maximum value of C minus x1 is unity, and so plugging this in here, we can say that x1 must be less than or equal to 1, because that's the largest possible value of C minus x1, over nk to the 1 over n. So if we know the size of an aggregate and the equilibrium constant, there is a critical concentration that cannot be exceeded for monomers in solution. If the monomer concentration exceeds x1, then all of the additional monomer goes into aggregates. This sets an upper limit on the solubility of a hydrophobic molecule. So if you put oil in water, entropy will allow the dissolution of a small amount of oil, even although the enthalpy, the binding energy, is raised by the breaking of hydrogen bonds. Nonetheless, the entropy gain is adequate to drive some oil into solution. But once you exceed the critical micelle concentration, all of the oil will go into a new phase, the oil that floats on top of the water. Let's take a look at the free energy associated with this process. In these equations here, mu10 is the chemical potential of a monomer, an isolated monomer. Mu0n is the chemical potential of a monomer in an aggregate of size n. So we can write the equilibrium constant down as the ratio of the Gibbs free energies. This is for n monomers, and the Gibbs free energy now for n times the monomer chemical potential in an aggregate of size n. And so we end up then with this expression here. Substituting back into the earlier result we found, we have then this expression for the concentration of aggregates. And we arrive at the following conclusion. The mole fraction of monomers, of course, must always be less than 1. So this is a number smaller than 1, and it's raised to n, the number of monomers in an aggregate. And so this will go to 0 rapidly as n increases, unless x of mu10 minus mu(n0) is a number greater than 1. This requires that this term here must be less than this term here. In other words, the chemical potential per particle in the aggregate must be lower than the chemical potential per particle in the monomer. So this is a required condition for driving the aggregation of my cells. So what is it then that reduces the free energy of a monomer inside an aggregate? Well, of course, the monomer is hydrophobic, and so it has a interaction energy with the solution that's unfavorable and proportional to the surface area of the sphere. Actually, the proportionality constant is the surface tension gamma. So that the free energy then is corrected by a term that depends on the surface to volume area of the aggregate. So that would be n squared for the area, n cubed for the volume, and we then divide this n to the 2/3 by n to get the energy per particle. So it goes like n to the 1/3 on the bottom. And then we have this energy here, 4 pi r squared gamma. Expressed in these terms, we can rederive the critical micelle concentration. This is done here. And the answer turns out to be that the critical micelle concentration in these terms is given by this exponential. So this says the larger the molecule, the bigger R, the smaller the critical micelle concentration. Let's actually put some numbers into this for adding oil to water. For a methylene group, the size of the molecule is around about 0.2 nanometers, and the appropriate surface tension or surface energy is 50 millijoules per meter squared. When this is done, the calculated critical micelle concentration as a mole fraction is about 2 times 10 to the minus 3. If we add more than 2 parts in 1,000 oil to water, the oil will then just aggregate into an oily phase that floats on top of the water. Why should the oil dissolve at all, even to 2 parts in 1,000? Entropy is the answer. The entropy of oil dissolved in a large aqueous phase overcomes the enthalpy cost of the hydrophobic interactions. Oil forms an uninteresting aggregate in water, but amphiphilic molecules form interesting shapes because of the geometrical constraints in their self-assembly. So, for example, if we have a large head and a small tail, you can see that it's natural to form a structure that has a curvature like this. The critical parameters are the length of the hydrophobic region, its volume, and the area of the head, from which you can form a dimensionless parameter, and the size of this dimensionless parameter can then predict the geometries that self-assemble in water.